Okay, section 9.4, power series. The most important series are power series. Okay, yeah, this series is called a power series with center A. Okay. And this coefficient C naught, C1, C2 denote the real numbers and called the center. The A is called the center, and these CI's are called the coefficient of the series, respectively. And X denotes the variable. Yeah, we are interested in criteria for the convergence of the power series. So when this series converges or not, okay. The power series always converges when x is equal to a. When x is equal to a, then these are all 0. So we only have C naught, which means the series converges. But in general, it may converge for some value of x and diverge for other values of x. For example, the geometric series is a power series with center 0. And we know this series converges if absolute value of x is less than 1. And it diverges if absolute value of x is bigger than or equal to 1. Okay, that's the typical example of a power series. Theorem 1. For a given power series of this, there are only 3 possibilities. The series converges only when x is equal to a, and series converges for all x. And the series converges in certain interval, and it diverges in the other intervals, which separate by the radius r. Okay. Definition on the radius of convergence. The positive number r is called the radius of the convergence of the power series. The radius, the positive number r, which was mentioned above, is called the radius of the convergence of the power series. The interval I that consists of all values of x for which the series converges is called the interval of convergence of the power series. It should be noted that the case of this case. This is not covered in the theorem. But, okay, so the reason was that some series may converge at when x minus absolute value of x minus is equal to r, and some series may diverge. So we cannot make any conclusion on that case. That's why it was excluded in the theorem. In general, the radius of the convergence R is determined by using the ratio test in which this R is the limit of absolute value of Cn over Cn plus 1, provided this limit exists. So we're going to use this ratio test or root test to figure out the case when the absolute value of x minus is equal to r. Okay. First example. For this series, find the radius of convergence and interval of convergence. So, yeah, here is the definition of interval of convergence. So, yeah, we were asked to find the radius of convergence and interval of convergence. For this case, since term an has looks like this, then by using the ratio test, we can find the limit of those ratios is equal to 0. What that means is the series converges for all x. In this case, the radius of convergence is infinity, and the interval of the convergence is the whole real lines. Okay. But for the second case, second example, which is the series summation minus 1 to n times x dn over n, and if we use the ratio test, then we have this term. Therefore, the limit of the ratio of this is the absolute value of x, which means this series converges when the absolute value of x is less than or equal to 1, and diverges when absolute value of x is bigger than 1. But so the radius of convergence is r is equal to 1. For the case when absolute value of x is equal to 1, we have to think differently. First, we consider when x is equal to 1, and then we consider when x is equal to negative 1. Okay. Okay. So when x is equal to minus 1, the series becomes a summation 1 over n, so harmonic series, so it diverges. This series diverges. Okay. When x is equal to 1, then this series converges because of the alternating series test. So the interval of the convergence does include that x is equal to 1, but does not include x is equal to 1, but it does not include the x is equal to minus 1. So we have the interval of the convergence, which is minus 1 to n, 1 with the open on the left side and close on the right side. Find the radius of convergence and interval of convergence for the series. And here, an is like this. So use the ratio test. Then we have this term. So absolute value, limit of that one goes to this. So all we have to do is this term. So this converges when this value is less than or equal to 1. So which means it converges when absolute value of x plus 2 is less than 3, and diverges when absolute value of x plus 2 is greater than 3. And then we think the end point, when the absolute value of x plus 2 is equal to 3, then we use, we have considered the case when x is equal to minus 5 and when x is equal to 1 separately. For the case when x is equal to minus 5, we use the divergent, the P series test, that says this is diverse, and for the case when x is equal to 1, we use the alternating series test that gives us the convergent of the given series. So the interval of convergence can be obtained by this convergent on when x is equal to 1, but diverges when x is equal to minus 5. So this is the answer that we are looking for, the interval of the convergence. The radius of convergence is 3. Okay. So all of the knowledge that we have learned for the convergence of the series can be applied to find the interval of the convergence and the radius of the convergence. Okay. Example 4. The function f of x is equal to 1 over 1 plus x cubed, and represent this function as the sum of the power series, and find its interval of convergence. Okay, here f of x equal 1 over x plus cube. Here, for this problem, here are some informations. Since we have the power series of the function 1 over 1 minus x like this, and we can use this knowledge for other functions like this. So if we use this knowledge, then we can substitute this x by minus x cubed. Then we can easily get the power series of this one from the known power series to get this, which gives us this. Okay. 무슨 말인지 알죠? 그러니까 이 파워 시리즈가 이렇게 생긴 걸 아니까 여기다 대체해서 바로 파워 시리즈를 따로 구하지 않고 도함수를 따로 구하지 않고 그냥 바로 구할 수 있다는 소리예요. Okay, so as you know, this converges when absolute value of minus x cube is less than 1, and so we can easily find the interval of convergence without much difficulty on it. Represent the function of this as a power series. Similarly, we just replace, we just change this. We know we have the 1 minus x like this. So, if we want to use the knowledge on the power series of this one, then we just change this one and replace the x by the 1 by 5 or 1 over 5, something like that. So, let's try to manipulate this one in this form. So, divide the factor out minus 5, and then replace x by x over 5. Then we can easily find the power series of this one, and then just multiply 1 over minus 5 to get the power series of the given one, which can be written in this way. So when this one converges, it depends on this value. So absolute value of this one, absolute value of this one, absolute value of this one. So we can easily find the radius of the convergence, which is 5, and the interval of convergence without much difficulty. Same thing on this one. X squared over x minus 5. Yeah, we can manipulate it in this way. X squared times 1 over x minus 5. And we know this one, we have found the power series of this one at the above. So, if we multiply x squared, it only changes the power in here. And the same thing, the convergence of this power series depends on the R, which can be obtained by the absolute value of x, which is 5. Then the interval of convergence should be minus 5 to 5, like this. So the knowledge on the power series of 1 over 1 minus x can be used widely. Any power series can be differentiated or integrated term by term within the interval of convergence, just as we able to do with polynomials. This is the one which is count. Okay. We can do just the integral and differentiation without any difficulties, but we have to consider all those things can be done within its interval of convergence, not outside of it. Okay, with those knowledge, that we can have the theorem too. Suppose this power series has the radius of convergence R, and then the function is differentiable and integral on the interval, and f prime of x can be obtained like this. Integral of f of x can be obtained like this, because it's all can be done by term, just term by term, and add all those terms. Both power series on the right side has the same radius of convergence. Okay, it should be remarked that the radii of convergence of the power series in equations 1 and 2 remain the same. Okay. But in the interval of convergence, I need not remain the same. That is, the end point of interval might change. That is it. So with those manipulation, the ratio of convergence does not change, but at the interval is same except those endpoint. Those convergence can be buried at the end of the interval of the convergence. So here is the example 7. Then find the radius of convergence of the power series representing f of x is equal to 1 over 1 plus x squared. Differentiate. So 1 over 1 plus x can be written in this way. Then we get differentiate of this one, get this one. Give us this one, isn't it? This can be exactly same as like this, which is the derivative of each terms, isn't it? Derivative of 1 goes to 0, derivative of minus x goes to minus 1, derivative of 2x goes to x squared goes to x, derivative of minus x cubed goes to minus 3x squared, like this, the summation. Hence, by multiplying both sides by minus 1, we have this one. So the radius of convergence of the power series representation is also radius 1, okay, because of this by theorem. Example 8. Find the power series representation of the function, this one, log function. This log function, if you find the derivative of this, then this is this. So the power series of this can be written in this way. If we do take an integration on both sides, then ln of 1 minus x can be obtained from here. So you don't have to do the differentiation on these to get the coefficient of all the terms in the power series of this. You can use the known knowledge to get the power series of these log functions. 이한별군? So this is a very the useful fact to use it in the interval of the convergence. Putting x0, so we can easily have to figure out this constant c, then let x is equal to 0 to determine the value of c, which makes the ln of 1 minus x is this. So with a simple factor, we can deduce lots of inequalities. Find the power series representation of f of x equal to arctangent x, then the radius of convergence. So f prime of x is like this. Then the arctangent of x can be obtained by the integral of this one, because the derivative of this one is this. So we just use the power series of 1 over 1 plus x squared to do the integration to get this one. And then figure out the constant c as 0, then in the same interval of with the same interval at the radius of convergence, that arctangent of x can be written in this way by integrating the polynomial term by term. And radius of convergence stays same. And radius of convergence, if you don't determine for this one, then we can use the CAS tool like this. If you to copy the address, then why don't we try here to get this is the radius, the radius of convergence. We may employ, we may use computer algebra system to test the convergence at the end point as well. So this gives us the radius of convergence. So with this knowledge, we can treat the problems. So I gave you the solutions here with the QR code and the web addresses. So you may check those answers and use this code to deal with other problems to share. Okay, that concludes the section 9.4. Okay. Any questions?